Hello, welcome to the next lecture about spectroscopy. And in these two upcoming lectures, we are going to dig into the ultraviolet spectroscopy for molecules. So we are dealing with absorption spectroscopy here. And in the first part, we are going to look how does the instrumentation for obtaining this kind of spectra look like. And in the second video, we are going to look at the spectra itself and how to perform quantitative analysis. So here we deal with absorption spectroscopy. This means that the molecules that we are studying are brought from their ground state to their electronically excited states. And we are primarily focusing on quantitative analysis here. That's for two reasons. First, because ultraviolet visible spectroscopy is used primarily for quantification. So qualitative analysis is simply not so often performed. And there are good reasons that we will find out during during looking at the different spectra. So what kind of properties of the radiation we are looking at? So we are looking at primarily at ultraviolet and visible spectroscopy. By ultraviolet, we mean the wavelength range of 190 to 400 nanometers. And this is the kind of light that we do not see with our eyes, but which is more energetic than the visible light. Even more energetic is ultraviolet light below 190, but with this we do not deal because this is called vacuum UV, and this comes from the fact that air molecules start absorbing light below 190 nanometers. So to do this kind of measurements, we would need very, very specific equipment where we would just get rid of all of the air. At the same time, below 190, almost all compounds absorb light. So these measurements would be very unselective and therefore not so useful, which doesn't mean that they are not used. They are used for specific studies of compounds, but generally from the selectivity point of view, this is not so, as useful as ultraviolet or visible spectroscopy. With visible spectroscopy, we mean the light in the range which we can see with our eyes. So what makes compounds and material around us colorful. And this is then from 400 to 800-ish nanometers. And the lower wavelengths start with violet light and end up with a red light. So all the rainbow colors. And even above that is near infrared spectroscopy, which can be an absorption spectroscopy as well, similarly to the ultraviolet and visible spectroscopy. And it has a few details that are very near infrared spectroscopy specific, but in general, it's quite similar. It needs a bit different equipment mostly, but it's not so different from UV-Vis spectroscopy. We deal with absorption spectroscopy here, and our analytes are molecules. So this means, again, a very wide range of molecules. Of course, neutral compounds, but also ionic molecules, as well as metal complexes with molecules or ions, can be studied with ultraviolet visible molecular spectroscopy. Let's now look a bit deeper into the instrumentation that can be used in ultraviolet visible spectroscopy. A very generic scheme of this instrumentation consists of a light source, a lamp, for example, a monochromator that is used to select the wavelength at which we try to do or want to do our measurements, a cuvette holder where we can switch between a sample and a blank, and a detector which then registers the light that is coming from the lamp, either through the blank. This is our reference beam. Or when we switch between the blank and sample, then the light from the lamp that is then selected by the monochromator, the exact wavelength where we want to do the measurements, passes through the sample. The sample is absorbing some of the light when the molecules in the sample go from the ground state to the excited state. Therefore, the light intensity of the sample will be lower, and detector can be is used to measure this intensity of the light then as well. And then later the computer does the calculations of how much light exactly was absorbed by the sample. The lamps that can be used can be different. So the simplest version would be to use a kind of similar light bulb that contains a tungsten wire. And this is actually possible for the visible range. So from somewhere 300 nanometers to a few thousand nanometers. So down to from the visible range essentially, or a bit below, to the infrared range. In ultraviolet range, deuterium lamp is very often used, which has a broad range that covers almost completely the ultraviolet range. And usually, classically, the instrumentation contains both of these lamps, so that the deuterium lamp is used when we want to measure in the ultraviolet region, and this classical light bulb is used when we want to measure in the visible light. And this is quite practical because when possible, we want to use the light bulb and do the measurements in the visible area. We'll see also why this is necessary. I can tell as a hint that the selectivity is usually better in this range. And therefore, we can turn the deuterium lamp on only if we want to actually do the measurements in ultraviolet range as well, because deuterium lamps are more expensive, and therefore the consumption of these is maybe a bit more limiting than of the light bulbs. However, now there is also xenon arc lamps, which cover the whole range of the ultraviolet visible spectroscopy. These are a bit more expensive, but very convenient to use if the whole range is very, very often scanned for many, many measurements that are being done. In addition to having a light source that generates us the ultraviolet visible light that we want to show to our sample, and where our sample can start absorbing the light, we also need to select the wavelength very precisely. And there are two general possibilities to selecting the wavelength. There is a photocolorimetry and the spectrophotometry. And these two types of ultraviolet visible spectroscopy actually are differentiated based on how we select the wavelength that we want to do our measurements. The photocolorimetry is a general name for the spectroscopy where we use filters to select the wavelengths that we are doing measurements, while spectrophotometry is the case where we use monochromator, and we do not just do measurements at one wavelength, but we usually scan through a range of wavelengths so we can get the spectrum information. In photocolorimetry, we use filters, and these can be, for example, colored glass filters if we deal with visible range. So essentially, they are just absorbing light anywhere, everywhere, but not in a relatively narrow band range. This narrow band range, however, is much, much wider than is for the monochromators. So this is the narrowest ones are 10 to maybe slightly below 10 nanometers and can be up to 100 nanometers. So compared to the whole range, they are actually they can be actually quite wide. And these filters with photocolorimetry do not allow us registering the full spectrum, but measuring the absorbance on this wavelength range that is passing through our filters then. On the contrary, spectrophotometers with monochromator can get much narrower bandwidth. This can be a nanometer range, and it can be used to scan through a specific range of wavelengths. So monochromator can be altered depending on the type of the monochromator, either turned, for example, to select the wavelength that we are interested in. So for example, if we have a deuterium lamp and light bulb combined instrument, and we have a monochromator, which is a prisma or a diffractometer, then what we can have is that we can actually measure the whole spectrum from 190 nanometers to 750 or 800 nanometers. And this, of course, enables us to receive more information about the compound or sample spectrum. However, for very many applications, the full spectrum is not needed. And in these cases, photocalorimetry is very convenient. It's also very much faster than scanning through the whole spectrum, as well as it is much, much cheaper because the monochromators are much safer. Or there isn't the need for a monochromator. We can use a much simple filter equipment. Now, when we move on in the instrument scheme, we have a lamp now, we have a possibility to select the wavelength, and now we need to have our sample. Our samples are usually liquid samples in molecular UV-Vis spectroscopy. We can sometimes have also gases, but mostly we have liquids. And these liquids are usually held in a cuvette. So this is essentially liquid holder, which has optical cuvette sides. So these are sides which are transparent to the wavelength at which we are doing the measurements. And therefore, depending on what is the wavelength range where we are doing the measurements, also the material of this cuvette is changing. So if we are doing measurements at ultraviolet region, then we definitely need a quartz cuvette, because the quartz is transparent also at the ultraviolet range. If we are good to go with the wavelength above 300 nanometers, then we can do measurements also in glass cuvettes. Quartz cuvettes are extremely much more expensive than glass cuvettes, and they are also more fragile. So this means that if we are above 300 nanometers, we usually don't want to use quartz cuvettes, just to be on the safe side. And most convenient is if our compounds are absorbing in the visible light range, then we can use plastic cuvettes, because ultraviolet spectroscopy is also is not possible with plastic, because most plastics that we can use here are absorbing ultraviolet light, but the visible light can come through our plastic cuvettes as well. What is important here is that the solvent also needs to be compatible with the material of the cuvette. So this is especially important in plastic. So for example, samples in acetone, even if you are studying colorful compounds, it is not possible to do the measurements in the plastic cuvettes, because the plastic cuvettes for ultraviolet visible spectroscopy are not acetone safe, at least not usually. The cuvettes have two optical sides. So these are sides from which the light from the light source is coming, that has passed through monochromator, and now it is entering to the sample from these optical sides. It passes through the sample, and then it exits from the cuvette from another optical side. So there are two parallel optical sides that will be put into the instrument perpendicular to the light path, so that the light can go through these optical sides. And it's extremely important that these optical sides do not contain any particles or fingerprints or any droplets or air bubbles, for example, when the sample is inside the cuvette. And this is important because these factors can cause scattering of the light that is passing through the sample. And additional scattering causes, of course, less light to pass through the sample. And what will happen is that the detector will just see that less light came through the sample, and our calculations would indicate that sample absorbed more light than it actually did, simply because part of this light was lost due to scattering. So all kinds of possible interferences that can cause scattering of the light that is passing through the sample should be minimized. So it's very important to take good care of the cuvettes that you're doing measurements with. And a good technique is to, just before measurement, clean the sides of the cuvette with either an inert paper or a specific cloth, and only then start doing the measurements, and also visibly see that there aren't any particles or bubbles or droplets on the cuvette sides. Additionally, also, solutions should not be foggy. So all kinds of particles in the solutions that can cause light scattering again should be avoided. Otherwise, the scattering will again be viewed as absorption, and our solutions will get a positive bias, so the concentrations will appear to be much higher than they actually are, because more light was absorbed, was not reaching the cuvette, but was actually not absorbed by our analytes. So this means that the solutions should be transparent. This means that suspensions, for example, can't be analyzed. So compounds, the samples really need to be fully dissolved. So if foggy samples actually do appear, but you know that the analytes that you're interested in have been dissolved, then it's very important to filter the solutions before doing the measurements with ultraviolet visible spectroscopy. Now, when we actually do the measurements, we have now the light that goes through the sample, and we have this passing through our sample, and we actually start getting the absorption measurements. And the absorption measurement we denote here by A, absorption, and it is calculated from the intensity of the radiation that came from the lamp through the monochromator to the detector if sample was not there. So if nothing was absorbing, and it is compared to the I, which denotes the intensity of the light when it passed through the sample. And important here is that we want to measure the intensity of the radiation before passing through the sample as accurately as possible. So meaning that it would be influenced by all of the same processes besides absorption caused by the analyte. So this means that, of course, it passes from the lamp to the monochromator, through the monochromator, and then to the detector. But ideally, this I0 should also be influenced by the cuvette and the solvent that we use in preparing our sample and holding our sample. So what we need is a cuvette which contains the solvent, or ideally also other additives that we have used in preparing our sample, besides then the analyte, and cuvette. And then we measure actually the I0 when the light from the lamp through the monochromator goes through this blank and reaches the detector. So this is how we obtain the I0. And the I, of course, is obtained when we are measuring the sample. When we talk about the blank, then it's important that the blank would be as similar as possible to the sample, but not, of course, containing the real sample. So this means the reagent, but also the cuvette. So the cuvette would need to be as similar as possible to our analyte. Sometimes we even can use the same cuvette. Why is the cuvette so important? Because even if the optical sides of the cuvette are made of a transparent material, there is slight reflection of the light from the sides of the cuvette, or also potential scattering when the light goes through the cuvette. The same for the solvent. There can be slight absorption by the solvent or slight scattering produced. And this tiny effects also are good to be taken into account. In some very rare cases, also zeroing with an empty cuvette before putting sample in can be used. But these are special cases where when we are very sure that we don't need to take into account any reagents or solvent. So how actually now to measure this I and I0? The simplest instrumentation is a single beam instrument where the I and I0, so intensity of the light that is going through the blank and going through the sample, are being measured separately. So this kind of instrument again contains a light source, a lamp, and a monochromator or filter. Mostly actually single beam instruments contain a filter. There is a shutter here that can stop the light from going through the sample or the reference cell. And there is usually actually also another shutter over here that stops the light from going to the detector when we are not actually doing measurements. So there can be two shutters here, which are useful to minimize the amount of light that is going to the detector. And then we also have here the measurement cells. We have a cell for the blank or the reference, and we have a sample. So these are the cuvettes that are holding our sample and our blank. And essentially what we do is that we just first measure the light intensity when the reference cell, so the cuvette with the blank, is on the optical path. So this is the optical path coming from the source through the monochromator, through the cuvette to the detector. And then we measure the I0, so the intensity of the light once there aren't any analyte molecules. And then we switch. We put the sample cell, so the cuvette that is carrying our sample, to the optical path, and then we measure the I. Otherwise, all the other things stay the same. And we, of course, can have an amplifier in the computer that does the calculations. A very simple, robust equipment, usually used with a filter to do very quick measurements with, for example, photometric reagents for some metal determinations is very common. A more sophisticated possibility is to measure the I and I0 with a double beam instrument. And there are two possibilities, the so-called in space and in time version. And let's view the in space first. What happens in the in space is that we have again one light source and a filter or a monochromator, most often actually monochromator with double beam instruments. And then we have a beam splitter here. So this beam splitter divides the beam into two equally intensive parts. One of these goes through the sample, and the other one goes through this blank cuvette, so a reference cell. From the sample, we measure the I, so the intensity of the radiation after passing through the sample. From the blank cuvette, we measure I0, so the intensity of the light that is not affected by the analyte molecules. And both of these are measured by detectors. So there are two detectors, one for one beam and the other one for the other beam. And later the outputs from these two detectors are combined, and absorbance is calculated with the previously mentioned equation. So A equals logarithm of the ratio of I0 and I. And lastly, from our computer, we usually get a readout. And when we use a monochromator, then we very nicely can scan through the whole spectrum in parallel for the reference cell and for the sample cell. We can also have a double beam instrument that is splitting the wavelength in time and not in space. And this is based on, again, the same light source in the monochromator, but here we do not constantly split the light, but we are actually using a kind of a grid that is consisting of an equal part of transparent and mirror plates, so that when it rotates, in one moment, the transparent part is on the light path, so meaning that light will go directly through and enter a sample cell, while when it turns a bit further, then the mirror part is what is the light quanti hitting, and then this light beam is mirrored to 90 degrees and directed to a reference cell, so the cell where our blank is in. And then later, these lights are also combined back together, or rather not combined, but alternatingly guided to a photodetector. So this grid over here is the same kind of grid as here, and or the combination is the same, and therefore one photodetector can be used because it's is measuring alternatingly the intensity from the sample and from the reference cell. The advantage of this compared to the in-space version is that both the I0 and I are measured with the same detector. So if there is any instability in the detector, then this is taken into account. Generally, when we compare the double beam with a single beam, then the advantage of the double beam is that we are always using the source. The light from the source is measured very closely in time between the I and I0. So if the source is, for example, becoming a bit unstable, either due to warming up or cooling down, something like that, then this is being very dynamically being taken into account by the double beaming time instruments. So now when we have this sample and the blank cuvette being also measured, we also need to detect how much light actually came through this blank or through the sample. And for this, we use detectors. And there are many different possible detectors. Phototubes and photoelectron multipliers are used in a very wide wavelength range, and they are still very much used, but they lack a feature called possibility to register multiple signal from multiple wavelengths at once. And this is overcome by diode arrays, which actually have multiple detectors next to each other, so that the spectrum can be registered with a blink of an eye from in the whole range that is of interest. But let's view briefly how these detectors work. So the most classical is a phototube. A phototube consists of a cathode that is covered by a photosensitive material and an anode wire. So here, and these are under a sufficient voltage. So the cathode is much larger, and the photon beams that come through the sample or through the blank is then directed to the cathode. And these photons are sufficiently energetic to pick out some electrons from this photosensitive material that is covering the cathode. And these electrons migrate to the anode, and this causes electric um, impulse, and then this can be measured by the direct current amplifier. A very simple system, similar system is also used for photoelectron multipliers, but here we don't have one electrode, but we have multiple. We have multiple anodes here. So the radiation is coming in from here, and it again hits a photo emitting cathode, so a cathode that is covered with a photosensitive material. And from here, electrons are being ejected as a result of the collision with the photon. And these electrons are being guided to Diode 1, which is actually an anode. However, because the phototubes are not super sensitive, the signal can be amplified here in the photoelectron multiplier. And this can be done by putting a next anode at an even higher voltage relative to the previous anode, just opposite to our first anode, and so forward. So we have here 9 different anodes which are at increasing potential to one another. So when one electron is emitted from the cathode, then this hits the anode, but from this anode, multiple electrons are emitted, and then these multiple electrons emit even more electrons from the second anode. And because of this increasing potential of the anodes, they are called dinodes. And in this example, we have 9 dinodes, and here in the very end, we have an anode that is then used to register the whole current produced as a result of this increasing electric signal. So we amplify the signal with the anodes. Lastly, it is also very important to remind you of the diode arrays. So these are essentially detectors, which look like plates here, but you can see that there are multiple electron connections down here in the bottom. And these are essentially like plates of tiny detectors. So what can be done is that the light that is passing through the sample can be divided in space by a monochromator, for example, Prisma, so that the lowest wavelengths that we are interested in hit this part of the diode, and increasingly the wavelengths start hitting the parts of the detector of the diode array, and the end of the diode array is hit by the wavelengths that are the highest that we are interested in. So with this, we actually instantly separate the whole range of wavelengths that we are interested in, and we also measure them all at once with the diode array. And this is very useful to measure the whole spectrum at once, and it is very often used in cases where ultraviolet visible spectroscopy is coupled with chromatography. This is especially important here because in chromatography, you have to collect the spectrum as fast as possible because of the constant separation of the compounds. The chromatography is something that we will view a bit later in this course, but from now, it's good to remember that the diode array enables measuring the whole spectrum at once, and this is used for ultraviolet visible spectroscopy as such, but also if this is used in combination with chromatography.